seemed like a huge lag, so I was wondering what was happening there. Okay. So, good afternoon everyone, and welcome to the live session for the course Mapping Signal Processing Algorithms to Architectures. The purpose of these live sessions is so that I can address some doubts as and when you are able to raise them, and if there are any specific parts that are not clear from the video lectures. Because one of the things, of course, that we need to keep in mind is the fact that the video lectures were recorded in a classroom where students would be asking questions, and therefore some of the portions over there may not be entirely clear to an audience who is viewing it offline, right? So what I'm planning to do for today's session is that I'm going to give a rough overview of some of the things that were covered in week 1 and a little bit of week 2. And also some questions have been raised by you, the audience, and I'll try and address a little bit of those. Not specifically going into too much detail. Of course, if you ask me questions over email, I'll try and respond to those also as much as possible. But for the time being, the purpose is more to sort of give you an overview of what this course is about. We'll be having these live sessions fairly regularly through the course, because I feel that that might be one way for me also to get feedback about how the course is going with you as the audience. So feel free to write in with your questions, and if there are any parts that you want covered in the live sessions, I'll be happy to go over those. So what I'm going to do now is just quickly start off with some of the things that what were covered in week 1 and week 2, and before that also just once again a brief review of what is it that I had expected of the audience in terms of the prerequisites and what was the purpose of assignment 0. Okay. So, oops. So of course, as you all know, I had explained the title of the course in a fair amount of detail, right? So the first lecture essentially went into this whole concept of what are signal processing algorithms, what are the architectures, and what is the problem of mapping that we are talking about over here. The course title, sometimes I refer to it as DSP algorithms, sometimes the signal processing algorithms. Primarily, of course, we are talking about digital implementation, so that's the main focus that we have over here, right? So in terms of the prerequisites, hopefully everyone is clear about what were the expectations, what you needed to know. In particular, the kind of things that I had mentioned and also given as part of assignment 0. One of them was the basics of digital systems, implementation. Then of course we have number systems and number representations, and as part of this I also went over a little bit of this in week 1, primarily concentrating on the floating point part of things, right? And then there was of course digital systems. The most important aspect over there is timing analysis, in the sense that do we understand what determines the speed at which a circuit can work and how fast it can work, right? So in fact, as part of that, we saw one of the assignment problems also had this question that was related to the clock period, the setup time, hold time, and so on. Hopefully all of you were able to work that out. And if there are questions related to that, feel free to either email me separately or bring those up even on the forums for discussion. So now what we had as far as week 1 was concerned, there are some of the topics that I want to sort of go over in a little bit more detail. So a few of the topics that we have covered so far, right? I'm just going to summarize them briefly over here. One of them is related, well, let's start from the beginning. So what are the things that we looked at? fundamentally we are looking at what defines a DSP algorithm and what are properties of DSP algorithms or problems that can be used in order to get better implementations in practice. When I say implementation, it could either be a pure hardware type of implementation where I custom design hardware from the beginning. The other one could be that it is a software implementation where I am basically writing some kind of C code which needs to implement this entire algorithm on some kind of a signal processor, or it could be a combination of both, right? But the DSP algorithm by itself has some fundamental properties that we could make use of, and some of them are, the fact that, for example, the rate of required operations is to a large extent determined by physical constraints. And what do I mean by physical constraints? What I mean over here is something like, for example, audio sampling rate at 40 plus kilohertz is sufficient, right? Now why is this? Because the human ear fundamentally is capable of distinguishing sounds up to a maximum about 20 kilohertz. That's even for the most sensitive ears, right? I mean, my ear probably can't even go close to 10 kilohertz. But even for highly sensitive ears, it's very unlikely that a human being would be able to distinguish sounds above 20 kilohertz. Dogs, on the other hand, can go well above that range. But we are primarily designing systems for the use of human beings, which is why we finally end up saying CD quality or high quality audio needs to be sampled at 44 kilosamples per second, right? So these kind of physical constraints are often a factor in DSP systems. Problem 1 in assignment 1 was in fact related to that, right? So when we had assignment 1, what we had was, for example, HD video, right? And the size over here I said was 1920 cross 1080 at 60 frames per second, right? Now, why is this considered high definition video? Because people have done a number of experiments and found that when I have video at this resolution and at this frame rate, most people would not really be able to point out any flaws in the picture. It's really considered high quality video, right? Having said that, clearly this is not enough, because nowadays we have 4K video where it's essentially double this resolution in each dimension, right? So around 3840 by 2160. So why is that required? Because at the end of the day, there are some people who are able to distinguish even finer features. More importantly, maybe we are going for even larger screens, right? And at the same time, we want to be able to make out fine details. So it's not that 1920 by 1080 is the end of the story, and you never need to go beyond that. But for all practical purposes, for a lot of scenarios, this would be enough. So one of the things that we want to do, that we should be able to do when we are analyzing a DSP algorithm is, can we analyze the computational and the memory bandwidth requirements of such systems based on their physical constraints, right? So as an example of this, basically problem 1 in assignment 1 would be something like, how many bytes per second would come down to what is the size of one image multiplied by 60, which is the number of images per second, multiplied by 4, which is the number of bytes per pixel, right? So the first one is basically pixels in one image multiplied by the number of images per second, multiplied by the number of bytes per pixel, and all of this put together would give you some number of bytes per second. Okay, Why is this useful? Because it allows you to sort of decide whether the basic hardware that you are thinking of and trying to build is suitable for your requirement, right? If it turns out that you have a memory bottleneck which is only, let's say, capable of doing 10 megabytes per second, it will almost certainly not be able to meet the throughput that you require over here. In fact, even 100 megabytes per second may not be enough for this kind of number of pixels that we are talking about over here. Okay. Similarly, we can go further and say computations per second How do we do this? Computations per output pixel into number of output pixels per second will give us the number of computations per second, right? So this is always a good way to break it up. It's sort of like, some kind of chaining operations together. If you want to find the total number of computations per second, let's break it up into things that we already have. What is the number of output pixels per second? Well, I want HD video, so the number of output pixels is 1920 into 1080 into 60 pixels per second. What is the number of computations per output pixel? Let's say that I'm doing a 3x3 convolutional filter. For each output pixel, I will need to do 9 multiplications and a corresponding number of additions. Okay, so you put all of those together and you end up with computations per output pixel into number of output pixels per second, and that gives you the total number of computations per second. Good. So the main point that I wanted to make over here, of course, was there are some fundamental properties of DSP algorithms, and the analysis of computation and memory bandwidth can be done without really knowing anything much about the architectures or how to go about doing this mapping. This is primarily common sense. Okay. Now, the next, in some ways, most important thing that we need to understand as far as the topic of this whole course is concerned is the fact that we are trying to do some kind of an optimization of an architecture, which means there is some cost metric that we are trying to optimize. Right? That's very important to keep in mind, because whenever we say optimization, you need to know what your cost is. What is it that you're trying to optimize? If you're not clear about what you're trying to optimize, then the statement basically does not make sense. Okay. The problem in our case is that it is something called a multi-objective optimization in general. Right? So what does a multi-objective optimization mean? It means that there are many different things that you might want to optimize, right? And how do you decide which one is the most important? So I think someone had actually raised this as one of the questions in the feedback. So I'm going to spend a little bit more time going over this. And this is of course related to that concept of Pareto optimality that I had mentioned in the first week's lectures. So hopefully it will make that aspect also a little bit more clear, right? The basic idea is something like this. Let's say that the problem is build, in fact, let's not worry about signal processing over here and say that we want to build a house. Okay. What are all the things that we might want it to be? We want it to be big. In other words, we are interested in the size of the house, let's say the floor area. We are also interested in how fast can it be constructed, and let's say the cost, okay, the actual rupee cost of building the house. So now what this means is we have 3 metrics that I might be interested in while building a house, and straight away by looking at it you will probably realize that they can be potentially mutually contradictory, right? So for example, getting a big house built fast is not easy compared to getting a small house built fast, right? So if I want to make the house big, also getting it done fast is going to be difficult. In the same way, if I want to make the house big, then the cost is likely to go up, right? Similarly, if I want to build something fast, one way of doing it is by pouring more resources into it, meaning that I ask more people to work on it, increases the cost. Okay, so you already have one scenario where I have three different metrics. Okay, now let's say that I go to different architects and each one comes up with a solution, right? So what do I mean by a solution? Architect 1 says I can build 3000 square feet in 1 year at a cost of 20 lakhs, right? I'm obviously making up these numbers. I don't think you can build a house for 20 lakhs, but maybe you can, or maybe not for 3000 square feet, but it doesn't matter, right? Architect 2 says I can build something which is only 1500 square feet. I will be able to do this, okay, let me do the same thing. Let me take the same number. I'll do the same 3000 square feet, but now I'll do it in 6 months and the cost will be 50 lakhs. Okay. Architect 3 might say that I'll give you a solution which is smaller, right? 1500 square feet, which I can actually do within 6 months, and it will cost you only, let's say again, 15 lakhs. Okay, so there's one problem that has arisen because of the choice of numbers that I came up with, which is when I'm looking at these three cost objectives, right, you first need to understand, are you trying to maximize or minimize these objectives? Okay, so generally speaking, what we would like to do is the size I want it to be as big as possible, right? So I want to maximize the area of the house, right? I want a big house, so obviously I want to maximize that area. On the other hand, I want it to get done as fast as possible, meaning that the time required for construction should be as low as possible. Similarly, I obviously want to keep the cost as low as possible. Okay, which means that I now have a situation where if I try comparing these three solutions, how do I do it, right? In terms of area, both of these have the same area. This one takes, so as far as the other metrics are concerned, this one is good, this one is bad, right? That is to say, architecture 2 is better than architecture 1 for the same area. Okay, but from a cost point of view, architecture 1 is better than architecture 2. So now which one is actually better, right? Assuming that I have decided that I actually want a house of 3000 square feet, should I wait 1 year and build it in 20 lakhs, or should I rush it through in 6 months for 50 lakhs? Okay, which one is better? There is no unique answer, and that's the whole point of Pareto optimality, right? The answer to this is it depends. If you have the money that you can pump in 50 lakhs, yes, go ahead and get it done in 6 months. On the other hand, if you can wait, you are not in such a big hurry, then get it done for 20 lakhs. You can save the remaining 30 for doing something else. Okay, so this is one aspect of a multi-objective optimization where the two things were contradictory. Let's also bring the next one into the picture. Let's try and compare these two solutions, right? Architecture 2 and architecture 3. Now what happens is both can be done within 6 months, right? One of them will have 3000 square feet and will cost 50 lakhs. Excuse me. The other one will be much smaller. It's only 1500 square feet, but will cost much less, only 15 lakhs. So once again, same story. Which one is better, right? It depends on what you want. If you are willing to accept the smaller house, then yes, the cheaper construction is better for you. Okay. Similarly, what we can do is we can also have a comparison between the first and the third, right? Which one is better? The first one has better area. It takes longer, which is not good, and it also costs more, which is not good, right? So the point is, what we can see is, even if I take only 2 of these solutions at a time, I already have different metrics on which one or the other does better. Okay, if I generalize this idea, what I can say is, now I'm moving away from the idea of houses. I'm looking for a problem, and I'm saying that, similar to the case of the architects who came up with 3 different solutions over here, now you as a hardware architect are going to come up with multiple solutions. Okay, and there are 2 cost metrics. I'll just call them x1 and x2. Okay, so in other words, if I do this, what I can say is, I basically have a two-dimensional plane, x1 on this, x2 on this, right? And what I want is, both x1 and x2 are to be minimized, right? So just like in this previous case, the speed and the cost, the time for construction and the cost were to be minimized. Same way, I'm considering x1 and x2 to be minimized in the next problem. If I wanted to maximize one of them, that's okay. I just need to take that into account in the direction in which I'm going to optimize. So now what I'm going to say is, there is one solution I have got, call it A, which has, let's say, some number 10 on the x1 axis and some number 40 on the x2 axis. Okay, there is another solution B, which has a larger number on x1, so let's say 30, and a smaller number on x2, let's say 20. Okay, I'm asking the same question again, which one is better, A or B? Okay, so the first thing that hopefully should be clear by now is, depending on which one is more important to you, you will have to decide, is x1 more important or is x2 more important, right? But the most common intuitive answer that people come up with in such a case is, why not apply some kind of weightage, right? And what we mean by weightage is, can I basically say, I'll multiply A by some, the cost for A by some values and add them together, so I come up with one single unique number, right? And the cost for B with some other set of values, so that I come up with another unique number, right? What I mean is, I'm going to take some kind of a weighted mean cost. So the weighted mean cost, if the weights for W1, let's say, is 0.5 and W2 is 0.5, right, meaning that equal weightage for both, what we are basically going to see is 0.5 into 10 plus 0.5 into 40, and this is going to be equal to 25. Whereas for B, it's going to become 0.5 into 30 plus 0.5 into 20, once again miraculously 25. Now what do? They're both exactly the same, right? Even though one of them has a lower x1 cost and the other one has a lower x2 cost, if I apply equal weightage to both the metrics, it turns out that I'm going to end up getting exactly the same net cost for both of them. Okay, but what if my weightage was different? Let's say it was 0.3 and W2 was 0.7. Now what I'll end up with is, A is 0.3 into 10 plus 0.7 into 40, so this is 28 plus 3 is 31, and B gives you 0.3 into 30, 0.7 into 20, that's 14 plus 9 equal to 23. Now which one is better? Remember, I'm trying to minimize the costs. B is better, right? And you can sort of see why that is the case, basically because I've given a higher weightage for metric 2 and B has a smaller value for metric 2, so B turns out to be better. The problem is, in general, you can't come up with a good set of weights, right? Because first of all, each of these numbers are going to have different metrics. Floor area is square feet, the time for construction is in months or years, and the cost is in rupees, right? How do you normalize all of them? How do you multiply them by weights? How do you add them together And finally, how do you come up with those weights in the first place, right? I will come up with one set of numbers, somebody else might come up with something else. To avoid all that, we sort of say, okay, if you can come up with weights, well and good, but if not, I should at least be able to tell you whether one solution is fundamentally better than another. The reason why that is important is, let me consider a third solution on this axis, let's say C, which has, let's say, 40 on the x1 axis and 30 on the x2 axis. Okay, now what can I say about this? B is going to be always greater than C. Why? Because x1 of B is less than x1 of C and x2 of B is less than x2 of C. Let me just correct this. I shouldn't be using the word greater than, I should say better than. Right? So, in other words, B dominates C. In other words, whenever I have two solutions, let's say one architect comes up with a solution B at 30,20 and another one comes up with C at 40,30, I can straight away say that B is better. I don't need to apply weightage, I don't need to do anything else. In every way that I can think of, B is better, right? It's like saying that I can now build a house for 4,000 square feet for 5 lakhs in 2 months, right? That's better than all the other solutions that all the architects came up with. Okay. On the other hand, what about A? A is a different story, right? What about A versus C? It's not quite as easy over there. x1 of A is less than x1 of C. That's good. But x2 of A is greater than x2 of C. That's bad. So A does not dominate B, or A does not dominate C. Okay. So if I wanted to sort of convert this into some kind of formal statement, I can express this purely in terms of this terminology that I have over here, dominance relationships, right? B dominates C, A and B are what we call Pareto equivalent. Neither of them dominates the other. Neither is completely dominant. And similarly, A and C are also Pareto equivalent. Okay, this is an important concept to keep in mind, because at the end of the day, the most important thing that you need to keep in mind while understanding a course like this is that there are no unique answers. You are not trying to come up with one solution which is perfect and which says, okay, this is the best possible solution for your problem. Excuse me. If you can come up with such a solution, well and good. But if you cannot, then you need to be able to at least say which ones are completely dominated and can be discarded, right? In this particular case, even though A and C are Pareto equivalent, I have another solution B. So as long as B is there in my mix, there is no point in retaining C, because anywhere where you would want to use C as the solution, you can always say, look, I would much rather go with B, right? It's also there. In all the metrics that I'm interested in, B is better than C. Therefore, it is a superior solution. Okay. Now, as a designer, when you are, let's say, trying to optimize the let's say the power consumption and the latency of a solution, right, of a digital circuit design. Once again, these are both metrics that I want to minimize. The way that you might go about doing it is, I come up with one solution over here. Okay. After some time, using the techniques in this course or using other methods, or just by reading some papers or coming up with some ideas or on your own, you find that there is some way to reduce the power consumption, right? But it increases the latency. and you come up with another solution S2. But after some time you come up with, let's say, a newer technology, right? It's able to reduce both the power and reduce the power without increasing the latency. So S3 comes over here, right? Then you find that I can also trade off and get an even lower power consumption, right? Or rather I go from S2 to S3, let's say, by making the entire system faster. I run at a higher clock frequency, but the technology has changed, so power consumption does not increase, as an example, right? Then I find that I can also reduce the power consumption while sacrificing some amount of speed, and I go to S4. I can do that once again even further and come up with S5, right? Or on the other hand, I can burn a lot more power and come up with something else, which is S6, which has a lower latency, right? So what happens is, initially what I had was, I had S1 and S2 as my solutions, and this dotted red line that I'm drawing over here is something called a Pareto front. This is what I originally had as my optimal solutions, right? But after I have come up with the other architectures, I find that this other line that I have drawn over here is the new Pareto front, right? Why am I calling it a Pareto front? Because each of these solutions, S3, S4, S5, S6, because of the way that I have drawn them, are Pareto equivalent. S3 is, for example, consumes more power than S4 but has lower latency. On the other hand, it consumes less power than S6 even though it has a higher latency, right? So on any pair of these solutions, I can find that if they do well in one metric, the other one will do better in the other metric, okay? And these Pareto fronts are sort of imaginary lines that join all of these dots together. Keep that in mind, they are imaginary lines. I cannot, for example, go and necessarily find a solution here, right? So is there a solution here at this point? Maybe not. We don't know, right? We can't say for sure. Just the fact that I've drawn a line over there doesn't mean that there are actual solutions at that point. So hopefully this sort of helps to clarify the question of how Pareto fronts can be generated, or how they are to be interpreted, more importantly. Okay. All right. So yeah, I'll just maybe go on to the next question. So I'll just excuse me. Yeah, so there are a few questions that I have got in the question session over here, and I'll just try and go over those in the time that we have remaining, right? Let me do one thing here. Okay, so one of the questions is related to how can for loops be implemented in hardware. Right? So in general, that's a tricky question. There are multiple ways by which it can be done, right? Later on, I'll be trying to give some demos of how we can use high-level synthesis tools in order to take C code and convert it into hardware. At that point, we'll also look a little bit about what kind of hardware is generated and go over that, right? But the basic idea of a for loop, there are two ways of doing it. Let's say that my for loop was for I is equal to 0, I less than 4, I plus plus, sum is equal to sum plus, sum a of I. Okay, what is this doing? It's basically adding 4 numbers together. What I can do is I can rewrite this to look like sum is equal to sum plus a of 0, sum plus a of 1 plus a of 2 plus a of 3, right? Which basically means it would look something like a0, a1, add them together, add the result with A2, add the result with A3, and I finally get sum. Right? This approach is something called unrolling. Right? What I have done is I have taken the for loop and I have unrolled it to get this equivalent new code. Right? The other approach that can be used for implementing hardware, and which is more general, right? Where the problem with unrolling is, what if instead of 4 this was 10,000, right? I can't create 10,000 copies of hardware, or maybe I can, but in general it's not a good solution, right? In that case, what I would do is I would have some kind of a adder which gets inputs typically from some multiplexers, right? And there will be one control finite state machine whose job is to send appropriate select signals to these, right, so that the right values get sent to the adder. One of those values, for example, could be the output of a register even, right? And the control finite state machine will basically have inside it, it will have a counter initialized to 0, comparator, check counter against some value n, and FSM will basically add, go back to increment counter state. Okay. In fact, I might even be able to do this with a single state, which means that in each state I will add 2 values, increment a counter, check whether the counter has exceeded its limit, and if necessary get out of the loop or continue in the same loop at the next set of values. Okay. So in terms of implementing for loops, this is one way by which you can do it. Okay. Hopefully that part is clear. We can also have further discussions, and I'll try to give more examples on the mailing list if this is not quite clear. Please let me know. There are a couple of questions that are related to, I think, the assignment itself. Maybe we can switch to this. So one of the questions was, I think, is one pixel going to be 3 bytes or 4 bytes? Well, there are different ways of representing it. In the assignment, I think I had mentioned 4 bytes because 32 bits per pixel. The reason for doing that is that typically what you have for color representation of images is that you use RGB, right? Red, green, blue, 3 different values for the pixels. Each one could be 1 byte or 8 bits. What is normally done, the reason why it is chosen as 32 bits is because you also include something called an alpha blending channel, which basically says if I have 2 images, then I can multiply each of them by some scaling factor and add them, and that effectively brings the sort of illusion of transparency into the picture. Okay, so that is why I had given 32 bits or 4 bytes. Okay, so 4 bytes per pixel is what I had assumed over there. 8 bytes per second was not really, I think, part of that question, at least for the question that I had in mind. It was 4 bytes per pixel, and the number of pixels per second, just as I mentioned a little bit earlier, you can compute based on the size of the image and the number of frames per second. Let me just quickly go over this. There is one question regarding pipelining and how it affects power or energy consumption. That is not a very easy question to ask, to answer in a very short time. So what I'll do is I'll try and see if I can give additional examples of that later. There is also a lot of coverage of that in the book by Keshav Parhi on VLSI signal processing, right? Various techniques that can be used whereby pipelining can be used in order to reduce power consumption. Okay, but getting into that sort of can be a fairly big digression on its own, which is why I'm not really going to get into that right now. For our purposes, the first and main reason why we are looking at pipelining is primarily from the point of view that I want to speed things up. I want to be able to run something faster than it was earlier able to do. Okay. There's another question about what is the best way to handle floating point numbers on FPGA. Good question. Now, what happens with floating point numbers? The main issue that you have with floating point numbers is, to put it very briefly, addition of floating point numbers is hard to do. Okay, multiplication of floating point numbers actually turns out to be a little bit easier than multiplication of fixed point numbers, because you have to multiply only 24-bit values as opposed to 32-bit values. So very often floating point multipliers can be slightly more compact than fixed point multipliers. But it's not as trivial as that. I mean, because of the fact that floating point also has like various different kinds of rounding modes and other kinds of complications, in practice floating point operations are always much more complicated than the equivalent fixed point calculations. Now on FPGAs though, it's not an obvious answer. I mean, typically in the past the answer was always, look, convert to fixed point and somehow figure out how to do it with a fixed bit width of operation. Nowadays, however, FPGAs are very good at handling fairly large numerical computations, which means that 24-bit multiplications and even floating point addition, including all the bit shifting, manipulation, all of that needs to be done, can happen in a fairly efficient manner with FPGAs these days. So to answer the question, if you can do it using fixed point, if you can, in other words, rewrite your MATLAB or Python or C code such that you can convert to fixed point before then writing the Verilog and implementing it on FPGA, that will always give you a better design from the point of view of both the area consumed as well as the power consumption, right? The cost that you pay, right, this is after all a Pareto optimal solution, right? There is a cost that is involved in that conversion. It's designer time. Right, you are going to spend a lot of time converting from floating point to fixed point. So if you can afford that, then yes, it is always worth it. Try and convert to a floating point, convert to fixed point so that it will work on FPGA. There may be some problems for which it just doesn't work, in the sense that the dynamic range that fixed point numbers give you is not good enough for the kind of computations that you have. Then you might be forced to use floating point. Nowadays, it turns out that especially with the high-level synthesis tools, writing floating point code and getting it implemented on an FPGA is actually very easy to do, right? The solution will not be as efficient in terms of area and speed as what you would probably get from fixed point, but it can be, from the designer's point of view, it can be done very fast and easily. So if that is your primary concern, how quickly can I get a solution? Use floating point, use high-level synthesis tools, implement on FPGA. If you require a better design at the cost of additional design time, go for fixed point. Okay. There is another question on, are VHDL inbuilt functions such as mod and log implementable on FPGA at clock rates up to 500 MHz? In general, you can't answer that unless you know which FPGA and what precision. How many bits of accuracy do you want, right? So the VHDL inbuilt functions such as mod and log, generally speaking, they will not implement very well on hardware, right? Especially if you just try using mod or log and try to synthesize it, the chances are that the compiler will come up with something which it is trying to get an accurate answer, which is finally going to end up being very big in terms of the area occupied and also not really very fast. But there are sort of approximate log computations and fast mod computations that may actually be possible to work at the kind of speeds that you want, maybe up to 500 MHz on the latest ultra scale FPGAs, right? But will have less accuracy, so they won't have 32-bit accuracy or the full floating point accuracy. They will trade off some amount of accuracy for speed. But if you are just trying to write the code and synthesize it, chances are you will not get those speeds. Yeah, the question about how to convert for loops to architecture, I hope I addressed that. There was also another question about, is it a good practice to write functions and use it concurrently in different processes, or is it better to write logic separately for each process? In my opinion, if you can write functions, I think that's actually good from the designer's point of view. And what will end up happening in practice is that the compiler will actually treat each of those functions, it will synthesize it separately in each context. So you don't usually incur too much overhead by using functions. Now this is especially true when you are using high-level synthesis tools. Even in Verilog or VHDL, if you use functions and use it in different processes, what will happen, the compiler will ultimately have to assume that two function calls are two separate pieces of hardware and will create the separate hardware separately for each of them and optimize it. So you don't gain or lose anything compared to having written the logic separately. But you do gain a lot in terms of the readability. The code will be better, right? Having said that, of course, you need to be sure that the way that you have written the functions is synthesizable, right? There are constructs that you can use in Verilog that make it non-synthesizable as well. So there was one more question for the Pareto optimal concept, whether we can take a 3D example. I don't want to spend too much more time on that right now. Hopefully, what we had over here. Yeah. Transition. Okay. Sorry, getting back to this. Hopefully what we had, so this example that I've shown is a 2D concept, right? Where I have only two metrics, power and latency, and hopefully the idea of the Pareto front is clear. But now let me look at the first example I had, right? Architects building a house. Okay. Now in this is actually a 3D example of Pareto optimality. Why am I not sort of using this in order to show Pareto optimality? Because it's much harder to visualize in 3 dimensions. That's all. That's the only reason. It's not that the ideas don't hold. It's just that I can't draw very well in 3 dimensions. Okay. But the basic concept that you end up with different points in space, and you are trying to then find an optimum value or an optimum wavefront corresponding to all of these, just like we have over here, remains exactly the same. One difference, of course, in the case of the architects building a house is that over here, power, latency, both of them I want to minimize. In the case of area, I want to maximize, which means just that, when I'm trying to minimize, what I will always have is optimal solutions are towards the origin. Right? But let's say that I was trying to build another solution where I have area of house and cost. Okay. Now what I have is cost should be optimized in this direction. Area should be optimized in the vertical direction, upwards. Okay, which means that my Pareto front will look something like this. I'll have one solution here, one solution here, one solution here. Right? And in fact, what we can do is this hatched area that I'm showing over here is essentially consisting of a part of the graph which says that any solution that I find over here is not good. It will be dominated by something on the Pareto front. Okay. So this is a case where I want to minimize the cost but maximize the area, right? So all I'm saying is that the direction in which you optimize becomes different. One small other thing which I think sometimes leads to confusion is to keep in mind that even though I draw that dotted line through the Pareto front, supposing I had 3 solutions, let's say S1 was here, it had values, let's say 10, 40, S2 let's say was 40, 10, right? And a solution S3 out here was 30, 30. Okay, the normal intuition sort of tells us that this should be the Pareto front. That's wrong. Okay, what is the Pareto front in this case? Is this one which goes through S3 also, because S3 is a Pareto optimal solution, right? So that dotted line can be very misleading if you don't draw it correctly. In other words, it should actually, rather than being a dotted line, it should only link together solutions that you are sure of, or rather it is not, there is no line linking solutions together. There are only discrete points in this space. Okay, this is the correct Pareto front because S3 is also Pareto optimal. Okay, just because I drew it a little bit inwards, right, doesn't mean that it becomes non-optimal, because if you look at it, compare it with S1, it is better on the y-axis. Compare it with S2, it is better on the x-axis, right? Sorry, this number, just to be clear, should be 10. Okay, so hopefully that part is also clear to everyone, and you sort of keep that in mind. Let me just quickly switch back to further questions. There's a question about computation of data rates in DSP. Hopefully that, the example that I gave with regard to HD video, I'm hoping has sort of helped to clarify that a little bit. There's a question about the relationship between logic gates and gate capacitance. Now, I do not want to get into this because that would be a course that would involve a big digression on the topic of digital IC design. It's not something that can be explained within a couple of minutes. The bottom line is that in general, more complex gates, the bottom line over here is that more complex gates in general are likely to have higher capacitance, right? So you can assume that a 3-input NAND gate, for example, will have a higher capacitance than an inverter, right? Which means that when it switches, right, it would probably require more energy to switch than an inverter. But beyond that, I can't really go into it in detail in this course. We can either possibly discuss it offline separately, or we could have, or I would strongly recommend that you look at maybe even one of the NPTEL courses that talks about digital IC design. There's a question about switching activity related to the number of clock cycles or any other in DSP architectures. Primarily what it comes down to is whether you're talking about a DSP architecture or a processor or a custom hardware or anything else, the moment it is built out of CMOS gates, you are interested in counting the number of times that a signal can switch from 0 to 1, 1 to 0, etc. Right? All of that becomes switching activity, which is relevant from the point of view of the total energy consumed by the circuit. So number of clock cycles, yes, because it will be related to the clock speed that you apply over there. If I have a high speed clock, more toggling, right, that will in turn become something that basically goes on for consumes more switching cycles and therefore more power, right? So hopefully that answers that question. There was one question about Xilinx Vivado synthesis reports and so on. Again, I have not really discussed Xilinx Vivado so far. I will try and give another video or separate session at some point where we talk about, where we go through a basic example of analysis, right? The problem that comes up over there, so the question is basically related to how accurate is the report. Well, the synthesis reports are fairly accurate in the sense that they use very good models of the FPGAs that are being used, and Xilinx is designing both the synthesis tool as well as the FPGAs. So their models, their data are very accurate. So from that point of view, the reports are fairly good. Having said that, when you actually implement it, you will find that there is some variability, right? And also the estimates for timing, power, etc. are somewhat pessimistic based on what Xilinx has used as numbers to make sure that they will meet the requirements that you have. So is it accurate? Reasonably, quite good, right? And you can actually use these. You don't need to sort of set big margins or anything like that. You can use the exact timing that you want, and it would have already put in its own safety margins to make sure that once it meets it in synthesis, it is almost certainly going to actually work on the board. Okay. There is one aspect that the one question has also come up about the sample interval versus the clock interval. Which I'll try to I will try to go over that a little bit briefly. The question was basically related to what is the difference between sample interval and clock interval, right? Normally what you have is DSP systems, sampling interval is what is important for us, right? Example for audio, what I have is, let's say that I'm dealing with 16 kilohertz audio, implies that the sampling interval is 125, well, no, 62.5 microseconds, right? So in other words, every 62.5 microseconds one new sample is coming in. But let's say that the hardware that I am building, right, some kind of processor for audio, right, it takes in samples at 16 kilohertz and needs to do some processing with it. I could perfectly well give this a different clock, let's say even at 100 megahertz, right? So what this means is, for every 62.5 microseconds, this corresponds to 100 system clock cycles, 625 system clock cycles. Why? Because the system clock is working at 10 nanoseconds, that is 100 megahertz. Okay. Now, what do I do with this? The basic thing that you can do with the fact that there is a separation between the sample interval and the system clock interval is the fact that 625 clock cycles are available to you for all the computations for one sample. Okay, and you can make use of this by basically saying, rather than using many different, even if I want to implement, let's say, a 10 tap or 20 tap FIR filter, rather than having 20 multipliers over there, I can use one multiplier and take 20 clock cycles or even 40 clock cycles to do the computation. I have 625 cycles available to me before the next sample arrives, right? So this is basically the primary difference between the sample interval and the clock interval. Okay, there is another aspect of it, which is the difference between the initiation interval and the latency, which also I think is covered in one of the lectures in that is over there. That also you need to sort of pay particular attention to and make sure that you understand it in some detail. Okay, so let me just see. I think most of the questions have hopefully been sort of covered to a large extent. We are running out of time right now, so I think I'll stop over here. In case you feel that some of the questions are not sufficiently clearly addressed, excuse me, please feel free to either post something onto the email discussion list, right, the discussion list which has been posted on the main forum over there, or you can also email me directly. I'll try and respond, but I think the email list is a much better way of asking questions, because not just there will also be teaching assistants and others who are familiar with the course material who may be able to respond more quickly and give you answers on that mailing list. Some of the other questions, especially if there are parts that are not clear, please keep the questions coming in. I'll try to have these sessions on a regular basis so that the doubts that are being raised over here can be clarified. Okay, so thank you all for joining the session. I hope it was helpful. If there are parts that could not be addressed due to the lack of time, then please let me know so that I can make them a higher priority to be addressed in the next session that we have. Thank you all for joining.